Heat generation problems have the potential to get really complicated if you're trying to find the temperature distribution inside the part of the wall generating the heat, because it's going to be parabolic, not linear. But if you're only interested in heat transfer, not the actual temperature distribution, then heat generation problems do kind of simplify to just thermal resistance circuit type problems. And so the key to this problem is making a good drawing. This is why I've got your TA Indy with me here today, because he loves making simple and effective drawings. And for this problem, if you have a good, simple, effective drawing, the whole rest of the problem is just going to fall perfectly, neatly right into place. And my recommendation for cylinder problems is to make your drawing as if they're just a regular wall. It's going to let you make a bigger drawing that's just a lot easier to see and read. And you just need to remember to actually include the cylinder resistances instead of the straight wall resistances later when it comes to actually plugging numbers into equations. And so to help with the drawing, your TA Indiana went back to his cylinder because we've got like a million different circles on this drawing. Where do we even start? Let's start right in the middle with the bright red, the actual heat source, the resistor. Right on either side of the resistor is the epoxy, like the coating on the resistor. If we look further inside towards the center of the cylinder, which I will mark as left on my drawing, we've got a steel pipe, and then inside that is water. So this is basically just chill water. This is what's providing the cooling to the resistor. The heat is going to flow from the resistor into the cooling water on the inside of the pipe. So essentially right now we could think we've got water in the middle flowing through a steel pipe, and on the outside of the steel pipe, there is a resistor epoxied to the steel pipe. But that's not enough. We've got on the outside of the resistor, we've got extra cooling because heat is going to go in both directions from the resistor. It's going to go inside and outside. So we need cooling on the outside also. So on the outside of the resistor, we've got more water and another steel pipe. So essentially we have two steel pipes, one inside the other, and water is flowing through both of them. The center pipe has a full cylinder of water, and the outer pipe has an annulus of water, where the water is essentially flowing between the epoxy and the steel pipe. Then outside the steel pipe is insulation, and outside of that would be the environment. So instead of little teeny tiny circles, I'm dealing with just big rectangles, like a big wall drawing, as if this is a big one-dimensional wall. So for lengths, instead of radiuses, I've subtracted all of the differences, so I just have the thicknesses. So on my wall drawing, these are just the thicknesses, not the radius from the center out to the point, the thickness of each section of wall. And now to help me understand what's happening inside the wall, I'm going to draw a temperature distribution that doesn't have any actual temperatures listed, it's just qualitatively accurate to help you understand what's actually happening inside this system. So the water is basically going to be at a constant temperature, I'll assume, if it's turbulent flow. But then right when it gets very close to the wall, there's going to be kind of a sharp uptick. And the actual wall temperature is going to be noticeably warmer than the temperature of the water. Then within the steel wall, it'll just be a linear line. Is there any other kind of line? So it's just a linear slope. The epoxy, again, it'll have a different K value, so a different slope. And I don't know at this point which one's going to be steeper or shallower, so I'll draw it shallower, but I'm just drawing a qualitative drawing just to try to understand the system right now. The actual shapes aren't super important. Within the resistor, there's going to be a parabola shape because the resistor is generating heat. Now, there doesn't have to be the same temperature on both sides. If there was the same temperature on both sides, the maximum would be directly in the center of the resistor. But because that doesn't have to be true, I'm going to draw it a little bit off center with one side of the resistor at a higher temperature than the other. It still has a parabolic shape, but my peak is now skewed slightly off to one side. And again, if this were a more complex problem, you might have to try to solve for exactly where that center is or exactly what these temperatures are. For this problem, I think that's not going to be necessary, but I'm just drawing this again just to understand qualitatively what it looks like. So since heat is generated in the resistor, there's some peak, And then it's going to get a little bit lower and lower towards the edges of the resistor. On the other side, a linear slope through the epoxy. The water outside the epoxy will be at a lower temperature than the epoxy, with a real steep sort of slope to get there. Then where the water touches the steel, again, kind of a real steep curve to get to the actual temperature at the inside of the steel. Linear slope through the steel, another linear slope through the insulation. And then I think we're done at this point because I don't think we care about what's actually happening outside of the insulation. So when I talk about making a good drawing will make the problem easier, this is the good drawing that you want to get yourself started off with. You've taken this really small circles and spread out and given yourself a nice big work area to work with. And now we can start to label temperatures. So we've got the temperatures of both flows of water, 47 degrees and 53 degrees. And so now I look at the problem statement again and ask, what am I trying to find? And it says I'm asked to find the temperature of the resistor. And so when I look at my drawing, my resistor is not at one temperature. My resistor temperature is in the shape of a parabola because it's generating heat. So it's not at one constant temperature. So the problem's telling me to make an assumption. The problem is telling me, assume that the resistor is actually at one constant temperature. And at first glance, that looks like a really horrible assumption because looking at my drawing, you can see that there's a parabola, like there are very different temperatures here. And since there's different temperature water on the inside and the outside, like there might be different amount of heats going in different direction. It might be different temperatures at the inside and outside of the resistor. But also keep in mind the size of the resistor. 0.001 meters, 1 millimeter. It might actually be that the resistor is so small that the temperature distribution is actually super tiny and this parabola is actually really short. It's not nearly as tall as I drew it. And so based on the really small size, it might actually be a reasonable assumption to just assume that the resistor is at one single temperature and that the parabolic shape is actually pretty flat compared to the temperature distributions in the rest of the system. And so I'll modify my drawing. I make the resistor just a flat horizontal line at TR. And hey, I'm never going to complain about making the problem a little bit easier by making a simplifying assumption. And so how am I going to find the temperature distribution? That's going to involve Q. Heat generation problems are always going to be about that heat that is generated has to go somewhere. So you're going to need to set up an electrical circuit to figure out where that heat goes. So for this system, since the resistor is in the middle, the heat is going to spread and go out in both directions. So I'll draw Q dot 1 going to the left towards the inside, Q dot 2 going to the right towards the outside. And now I'm drawing my Q dot 2 only up until we get to the water. And the reason I'm going to stop there is because that's where temperature is known. For this problem, I don't actually care about the steel or the insulation on the outside. So when using an electrical circuit analogy technique for heat transfer, your V equals I times R, the voltage, is just going to be change in temperature. So you're only interested in the resistances between two known temperatures, or in this case, a temperature I'm trying to find. So I'm interested in Q from the resistor to the water, both on the inside and the outside. So I don't care about the Q in the steel and the insulation because I don't even know any temperatures out there. So there's no way for me to find out how much of Q2 that goes from the resistor to the water. I don't know how much of it is sort of swept away by the water and how much continues through the steel and the insulation out to the atmosphere. That's not relevant to this problem. I only care about what's happening in between the known temperatures and temperatures I'm trying to find. So I'm starting off my solution just with essentially a conservation of energy. Q dot, the total heat generated, is equal to Q dot 1 plus Q dot 2. All the heat generated by the resistor has to go somewhere. Some of it goes inside, some of it goes outside, but however much is generated, it goes in one of those two directions. So Q dot equals Q dot 1 plus Q dot 2. Now I'm given the total amount of heat. That's a 9.4 kilowatts per meter, where the meter is sort of the direction into the page, like the length of the resistor, right? This is like the length of the pipe. So just like V equals I times R, Q, heat and heat transfer, is like current. It's the thing that flows. So if I take V equals I times R, I can rearrange that. I equals V divided by R. V is my change in temperature, R, thermal resistance. So I'm replacing my Q dots with delta T divided by thermal resistance. And again, I can completely ignore Q dot 3 because I don't know how much of Q dot 2 actually proceeds through the wall versus how much is like swept away by the flowing water. So let's plug in what we know. We've got the 9.4 on the left. On the inside, we've got temperature of the resistor minus the 47-degree water. And on the outside, temperature of the resistor minus the 53-degree water. Now for one-dimensional conduction for Q dot 1, that's going towards the inside, all of the resistances are in series, we can just add them all up. A nice assumption that you can write down is that we're going to be ignoring surface contact resistance. So where the resistor meets the epoxy and where the epoxy meets the steel pipe, there could in theory be an extra resistance called surface contact resistance. So it might be that the surface of the epoxy and the surface of the steel pipe are not actually at the same temperature. Because there's actually sort of slight gaps in between them, like at the atomic level, it might be that the epoxy is actually a little bit warmer and the pipe is actually a little bit colder, which allows heat to jump across those gaps, essentially. But for this problem, we're not given any information about that, so we're just going to put an assumption. Ignore surface contact resistance, which is a good way to show your professor that you have a good understanding of these types of systems. So the only three resistances we're going to include on the inside is going to be conduction inside the epoxy, conduction inside the steel pipe, and then convection from the pipe into the water. These equations for these resistances are definitely in your textbook. I'm going to grab them from the FE reference manual. For convection, 1 over HA. And for conduction through cylindrical pipes, you have to use this natural log equation. You can't just use the L over KA like for regular through a straight wall. Even though we made the drawing look like a wall, that was just as a visual aid. Remember, this is still a cylinder, so we have to use the cylindrical thermal resistance, right? And the two are different because on a regular plain wall, there's the same amount of surface area on one side as the other. But for a cylinder, for a pipe, there's less surface area on the inside and more surface area up on the outside. So it's not, strictly speaking, perfectly one-dimensional, which is why there's the extra natural log accounting for the difference in the inner versus outer radius. So now I was so proud earlier that I just wrote down the thicknesses instead of the actual radius out to each point, but now that I'm needing to put actual radiuses, radii, into my equation, now I need to go back and edit my drawing a little bit to put the radius kind of at each interface. Okay, so for the 1 over HA, I've got H of 1400. The area of a cylinder, 2 pi r, that's the perimeter, times the length. And then I'm plugging in 0.03 and 0.025 is the outer and inner radius for steel, along with the K value of steel that I was given in the problem statement. Then for the epoxy, 0.033 and 0.03 outer and inner radius. And 0.5 is the K value for the epoxy. I'm going to multiply every term by L just to sort of get rid of it for now, but in actuality, I'll probably just plug in a 1 for it later. Just assume a 1 meter length of pipe. But for now, I get 0.03696 as the resistance, thermal resistance on the inside of the pipe. Similar sort of thing, but now we're going to go from the resistor out. This is going to be for Q2. On the outside, we just go through epoxy straight into the water. And again, we don't care about the steel or the insulation, just epoxy, water, 53 degrees, done. So this is still in series, so I'm just going to add up the two resistances. Through the epoxy is going to be the natural log, because again, epoxy is a cylinder, even though I drew it as a wall. And then convection out into the water, 1 over HA. So 0.037, 0.034 are my two radiuses, 0.5 as K for the epoxy, and still 1400 for the convection coefficient. Put in a new outer radius for the outside radius of the epoxy for the convection, right? 2 pi RL for the outer surface area for 1 over HA. Calculator work about 0.026 as my thermal resistance for Q going outwards from the resistor towards the annular water flow. So since our answer is going to be per unit length, we can just plug in 1 for L, since the length is sort of unknown, doesn't really matter, and that will eliminate it from the equation. And now before I do all the calculator work, I'm going to write down my units to make sure I'm not making a unit mistake. And of course, I was about to make a unit mistake here. My 9.4 is in kilowatts. But if I look over on the right-hand side, my value for K was using watts. So I actually need to use 9400 on the left-hand side. I need to be in watts in order to make the units cancel out. So I multiply both sides by the denominators, the 0.036 and the 0.03. So now I just have like an inline algebra equation without any fractions, and that will make the algebra a lot simpler the rest of the way. So I'll group together my TR terms, then some calculator work. 205.9 degrees Celsius. Box it up, final answer. To figure out whether or not this makes sense, we know for certain that since the water is 47 and 53 degrees Celsius, that the resistor has to be higher than those two. If we had got an answer between 47 and 50 or less than 47, we would know that that would not make sense because heat flows from hot to cold. So you expect the resistor temperature to be higher than the temperatures of the water that is cooling it. So a lot of circles in this problem. If you're TA Indiana back on his circular hamster wheel, if he helped you out a little bit, go ahead and hit the thumbs up and that'll let him know that he's doing his best. And if you're ready for a harder heat generation problem, one where you're actually trying to find temperature inside the part of the wall generating heat, that's the video linked up on the screen now.